I think we're good to go now. Hello and welcome everyone to the most awaited space talk, which is based on the first image clicked by the James Webb Telescope. The James Webb Space Telescope was launched in December 2001 and is now all set to release its first operational images on 12th July 2022. So, to celebrate its success, we at Hex-Star Universe have brought to you three live talk sessions. The golden eye opens, the James Webb Telescope begins. To showcase the telescope's powerful instrument and review the scientific mission to come. Our speaker for today is Dr. Priya Hasan. She is an assistant professor in physics at the Maulana Azad National Urdu University, Hyderabad, India. She did her integrated masters from the Moscow State University, Moscow, Russia, PhD at Osmania University, Hyderabad in 2004, and postdoctoral research in France and IUCAA, Pune. She was awarded the Woman Scientist Award by DST in 2006. She has presented her work in various conferences in India, Europe, and US, and in the United Nations, Vienna. We are pleased to have we are pleased to have Professor Rajat Kumar Pal from University of Calcutta, and we are really thankful to him from the bottom of our heart for joining us in today's session. So, without further ado, I'd request Dr. Priya Hasan to start with today's session.
Thank you. Thanks, Somadip. Uh, Everything is fine, right? You can hear me well? Hello?
Yes, ma'am, you're audible.
Yeah. Okay. Yeah. So, hello, everyone, and good morning. And today I'll be talking to you about the James Webb Space Telescope. The golden eye opens. And basically, because today is a very important day in the schedule of the plan of James Webb. And I'll tell you more about it as we go forward. So, people who do have questions or anything else, you can ask me at the end of the talk or during the talk. And otherwise, you can always email me at priyahasan@gmail.com. Okay. So I've got to first start with this very small movie, but something which is very beautiful. I really find this. But in today's times, we've reached a time when science fiction is actually reality. Things that we thought is not possible. I'll show you this little short video on the James Webb Telescope, which will actually convince you that we've actually reached a time when science fiction is reality in our time. So over here, this is the Ariane Rocket Center, which is in Guru, and this is where we are seeing the launching of the telescope. You can see, like in this telescope, you can see that the James Webb Telescope is a 6.5-meter telescope. So it's huge, and it has sun shields which are the size of a tennis court. So in principle, no rocket can actually fit such a huge thing. It's like a two-story building, and therefore you can see that the telescope was actually folded and put into this thing to be launched, right? So you have the first thing which comes up with James Webb, that you had to literally fold a telescope. I mean, imagine how strange that sounds, but that's exactly what's happening. So you have a folded telescope kept over here, up here, and that it gets launched. This was launched last December in 2021, 25th of December. And you can look at this thing. You have this massive, here your rocket sits over here, and it's a multi-stage rocket. So what are multi-stage rockets? This is Kuru, and you can see that the launch took place. And we don't have time to talk about today, but we have what are called multi-stage rockets. So you see these parts of the rockets are basically things which have the fuel, right? So you can see that as the fuel gets used, the rocket actually throws the fuel, this thing, back into the ocean. So typically you have this on the east coast of countries, where you actually, as it gets launched, the earth rotates, and the lower part is where the sea is, and you keep dropping these different components which have the fuel for the rocket as the launch takes place. So you can see that there's multi-stages, various stages where the different parts are thrown back, which have the fuel in them, which are used, and then finally you have the module which has the telescope, which actually is, thrown out of the Earth's orbit, right? And that's where it gets thrown out. And you can see that this is the way it makes its journey into space. And like I said, this telescope is made up of 18 segments, which are four. So you have the last piece falling off, and this was the last we actually saw of the James Webb, where you had the last of the telescope on it. All right. And you actually have an unfolding of a telescope taking place, which took 14 days. So you see here the sun shield opens out first. This is the solar panels, then the sun shield. It has to open out and it kind of unfurls, right, itself. And this is basically to protect the telescope. The telescope is an infrared telescope. I'll talk to you about that in a minute. And you'll see that this thing actually opens up, right? It actually unfolds. This is the shield, which actually is in 5 layers. So you have 5 layers of the shield, which opens up, right? And here you have, this is the primary mirror, the secondary mirror, and it actually unfolds and comes out like this. So you can actually see that this is, I mean, as good as science fiction can actually think up, where you have a telescope made up of 18 segments, which actually opens up. This is the primary mirror, this is the secondary mirror, and here you have the sun shade, right? And that's the way the telescope actually unfurled. But before let's try to understand the whole telescope. And for that, I'll actually have to start a little earlier with my story. So I will actually start off with the story of telescopes, right? How do we actually think up telescopes? And even more importantly, how did we actually start sending telescopes in space? And why do we actually have to do that? Why do we have to send a telescope in space to, get better observations, obviously, but I'll tell you why and how. So the story of telescope starts about 400 years ago when Galileo was the first to actually use the telescope to look up at the stars. And this itself was a very important moment in history or the development of science because what Galileo saw were actually things which were not very pleasant for the church and they were actually very path breaking things. For example, he saw the craters of the moon, right? And the moon was considered a celestial object which was supposed to be flawless, and you had craters on the moon. He saw the phases of Venus, and the phases of Venus could only be explained if you could have the orbit of Venus within the orbit of the Earth, which was against the heliocentric, the geocentric model of the universe, which was at that time considered. The geocentric meant that the Earth was at the center and the sun was going around the Earth. But the phases of Venus showed that it could not be like that if you wanted to have phases. You had to have the Venus within the orbit of the Earth to explain phases. The next thing which he also saw is he saw the satellites of Jupiter. So he actually saw a system of satellites going around another object, which was Jupiter, which was against contrary to what the church believed, because they believed that everything essentially is going around the sun. And that is why what Galileo, though the telescope he used was a very small telescope, but even with that, what he observed was so very revolutionary, which, actually convinced people about the importance of actually using telescopes to look at celestial bodies. Now, the other important thing about space and telescopes is that what we look with our eyes, which is called visible light, is a very small portion of the electromagnetic spectrum, which is this very small portion, which is, say, between 3,000 to 8,000 angstroms. That's all we can detect with our eyes. The rest of the universe, which has radiations in gamma rays, X rays, infrared, in radio, etc., these are not detected by our eyes. And therefore, we have to make very special kind of telescopes which can actually detect radiations in other parts of the electromagnetic spectrum other than the optical part. So, and therefore, we actually needed to have a revolution in actually looking at these other parts. And these other parts are important. Why? Because visible light is only a small fraction of the electromagnetic spectrum. And there are different physical processes which are observable in different parts of the electromagnetic spectrum. And you obviously need to explore this to study different kinds of phenomena. And the problem, what happens is that it's not the problem, it's the blessing we have, which is the atmosphere. The Earth has this layer above us, which is the atmosphere, approximately till a height of about 100 kilometers. We have this thing, it exponentially falls. So in principle, it goes on till infinity, but we kind of consider it to be within 100 kilometers. And what happens is the atmosphere, which protects us, which actually is the basis of life on our planet, it actually blocks radiations. So, for example, X-ray and ultraviolet radiation, our atmosphere is completely opaque to it. It cannot pass through our atmosphere, which is a godsend for us, because otherwise life would have not existed on the earth the way we know it. The visible window is the part in which light comes through the atmosphere. And then in the infrared, we have small windows or pockets in which we can have certain wavelengths which we can observe. And then there are some parts of the wavelength which we cannot observe. Same with the microwave. And then the radio, that is the biggest window which we have, which the atmosphere lets passage through. And then again, when you go to further longer wavelengths, again you have a block. So the problem with the atmosphere for us is life giving. Life exists on the earth because of this. On the other hand, the problem is that because of this thing, we we cannot observe these parts of the electromagnetic spectrum because of our atmosphere. And to show you why is it important to look in different wavelengths, you can see over here, I'm showing you images, for example, here of our galaxy in different wavelengths. And you can see that there are different components of the galaxy which are observable in different wavelengths. So for example, in visible, you see the stars. In X-rays, you see hot gas. In radio, you see other elements. In infrared, you see the colder gas. And that's why it's very important for us to see our galaxy in different wavelengths so that we can see different components. Similarly, in this image, you can see different components are visible in different parts of the electromagnetic spectrum. And for example, if you were to look at a single galaxy, the Whirlpool galaxy, here you can see how would it look in radio, in infrared, in optical, in ultraviolet, and X-ray. So in radio, you can see the gas around. In infrared, you can see the cooler stars. In optical, you can see the sun-like stars. In ultraviolet, you can see the hotter stars, the hot components. And then in X-ray, you can see hot gas. And therefore, if we want a true picture of our galaxy, we need to see it in all these wavelengths so that we can understand the galaxy in total. Because that otherwise we would be like the blind men or the women, where we would just have a certain picture of our galaxy. And if we want to actually piece the puzzle as to what actually makes up our galaxy and what's actually happening in our galaxy, it is necessary that we see these different components, like the gas component, the hot stars, the cold stars, and different things to piece in the puzzle of what our galaxy is all made about. The other important thing about the atmosphere is that the atmosphere obviously has turbulence. So, for example, if you were to look up at a star from the atmosphere, you know that there is turbulence in the atmosphere, there are winds, there are things happening, due to which the position of the star moves, which is what we call twinkling, right? The position of the star moves, and therefore we cannot see very accurately. So, the position of the star actually gets smudged over a region, and we actually think the star is located like this, and therefore this is what we call in astronomy seeing. So what happens is that since the atmosphere refracts starlight in random directions, it causes stars to twinkle. And if you were to look at it through a telescope, the position of the star will move, in which you will actually think that the star is taking this whole region, right? If you are on a mountain top where there is lesser atmosphere, you will have less of this shift, and therefore you will see the image of the star moving lesser. You'll be able to see it much more, you know, much more clearly, which is something like this. For example, if you look at an image of Jupiter, if it is with a lot of atmospheric refraction, you will see it smudged. You will not be able to see detail on it. While if you see it through a telescope or through a better sight up a mountaintop, you will be able to see detail on that image. Similarly, over here, you can resolve. This is what we call resolution. You can resolve these individual stars over here, but over here, you are seeing a smudged image. Another example being over here. And therefore, what happens is, anyway, we know that light is a wave. And therefore, when you look at any object, you will have a certain amount of smudging which takes place, which is called diffraction limited seeing. So even if you had a star, it actually, because of diffraction, the light of the star gets spread around. This is what is called the Aries disk, the upper part, this disk. And then you have the spreading out outside, right? And this, so in principle, because of the wave nature of light, you do have a certain smudging, which will anyway take place. There is no way in which we can avoid this smudging. But there is additional smudging which is happening because of our atmosphere, right? And therefore, it becomes very important for us, number one, to have a telescope like I showed you, and number two, to send the telescope out in space. So the first reason being is that certain wavelengths have to be accessed from outside the atmosphere. For example, if you want to observe an X-ray, gamma ray, ultraviolet, infrared, you have to go outside the atmosphere. The second reason is that the atmosphere smudges your seeing, and therefore, if you go out in space, you will be able to see much more clearer images, and you will see the certain smudging, which is called diffraction limited seeing, but it's still the best image you can get. The other thing is that ground-based telescopes, they have limited observing time because of the Earth's rotation. While if you have a space telescope, the space telescope can observe 24/7, right? Because you do not have a problem happening because of day and night sequence, right? You can always position the telescope in such a way that the telescope is always in a part of the sky which does not have day, hence you can observe all the time. And therefore, space telescopes are a very good, improvement in our capabilities of observing. And they could actually be of two kinds. They can be what is called a survey mission. So a space telescope, which is a survey mission, it just keeps observing the sky all the while, and keeps giving you data. Or it could be targeted observations. That means the telescope only observes certain targeted parts of the sky. This is basically because a telescope has a smaller field of view. And therefore, if you want to look at the whole sky, it would take you too long. And therefore, but you have very big telescopes, for example, like the James Webb. In that case, you only observe certain parts of the sky or target observations, depending upon your requirement. The disadvantage of space telescopes, however, is that obviously they are very, very expensive because a telescope itself is expensive compared to a ground-based, any telescope, even ground-based, is very expensive. And then the other thing is that because of their location, you send them out in space, they are very difficult to maintain. So I'm sure you've heard about this Hubble Space Telescope. The Hubble Space Telescope is relatively close by. It's just at a distance of about 550 kilometers. So you can service it. There have been various service missions of the space telescope, but obviously every service mission costs a lot of money and requires a lot of planning. So first thing is launching the telescope and then doing service missions, which obviously cost money and take a lot of planning and a lot of effort. So that's the problem with space telescopes. But obviously, space telescopes are very advantageous. So way back in 1837, Beer and Madler, these were two people who actually discussed the advantage of actually having an observatory on the moon. We know that the moon has a very thin atmosphere, rather it almost doesn't have an atmosphere, and it's close by. And therefore, if you were to have an observatory on the moon, it would actually be very good because you won't have a problem of atmospheric seeing, as well as it would be close enough. And then in 1946, Spitzer, he had actually proposed having a telescope in space, and people started considering the possibility of having telescopes in space. And various space telescopes were actually conceived. This is a montage of various space telescopes which have been launched, and people actually started thinking this as the possibility of doing this. And the first one that you've actually heard a lot about it is the Hubble Space Telescope. So the Hubble Space Telescope was actually launched as a space shuttle and was launched in 1995. And you can actually see that the images that Hubble sent back, right? It's literally out of this world. You can see these are some examples of images of the Hubble Space Telescope, which are really mind blowing. These are images which you even now they're really beautiful images which we got. So Hubble is a relatively smaller telescope. It's only 2.4 meters in size, and but these are the kind of images we got using Hubble Space Telescope. There were another set of telescopes, for example, the Chandra Telescope. This is a telescope which specifically observes only in the X-ray. And like I told you, that X-rays do not pass through our atmosphere. So if you want to observe it, X-rays, you have to have a telescope out in space. And this was named after Chandrasekhar, the Indian astrophysicist, who got a Nobel Prize also. And so the Chandra telescope, which is an X-ray telescope, is very much still operational. It has four excellent instruments on it, and it looks at high energy phenomena. For example, X-rays, active galactic nuclei. And here you can see some examples of the images which we've actually got with Hubble. This is a short video where you can actually see the kind of images that Hubble gave, which are mentioned over here. There's a supernova remnant, which you have SN 1987A. You have this is the Cartwheel Galaxy. This is the Helix Nebula. And these are really beautiful images. Some of these images are actually made up of two images. The bluer part is the one which is got from the X-ray. Some of them are overlaid with optical images too, and they're very beautiful images which you got with the Hubble Space Telescope. Sorry, with Chandra. And there was a gamma ray observatory called Compton, which looked in gamma rays. And then there is an X-ray, this is an infrared observatory called Spitzer, which has a size of only about 0.85 meters. And it actually observed in the wavelength range of 3.6 to 160 microns with excellent instruments on it. And this is Spitzer. Herschel was another telescope, which was a 3.5-meter telescope, which could observe again in the far infrared and the sub-millimeter wavelengths. This is an example of the image of Herschel taken of M31 Andromeda Galaxy, which is the closest galaxy to us. And you can see how good it is. NASA also had a great observatory program that they actually observed at portions of the skies using all these telescopes, the Hubble, Compton, Chandra, as well as Spitzer. And they had what was called the goods field, where they observed the same parts using this. There was also a telescope sent out in 2009, specifically to look for exoplanets, which are planets outside our solar system. This was called Kepler, and it basically looked for these things. A sequel to Kepler came up in 2018 called TESS. TESS is also a planet hunter whose job is basically just to look for exoplanets, and it was launched in 2018. It's still operational. It has found a large number of exoplanets, and there's very good research being done based on this. Now, astrometry is actually the accurate measurement of the positions of stars. So here you can see a video. This is a movie of the Big Dipper or Ursa Major, where you can see that each of the individual stars, they actually move. And these movements are very, very small movements, and they have to be very accurately measured if you want to know the motions of stars. And therefore, to study astrometry, the first mission, which was again a space mission, which was Hipparchus, which actually looked for this, and it actually measured what is called parallax, which is the precision of this thing. And the sequel to parallax is okay. So what it does, it very accurately measures space velocities, which are called proper motions and radial velocities. We won't talk in details about this, but essentially this gives you three-dimensional motion of stars to tell you how stars are moving. And this is something very, very difficult to do because these motions are very, very small because of the large distances of stars. And then the present ongoing mission, which is called the Gaia Mission. This was launched by the European Space Agency, which actually accurately measures, the motions of stars. Now, a Gaia, since it is actually having to measure this very accurately, it is positioned in a point called the L2 point, which is the Lagrange point. So Lagrange points are points where the gravitational attraction of the Earth and the Sun are balanced. And the Lagrange point is where the Gaia mission sits. It's at a distance of 1.5 million kilometers. So this is very, very far away, where obviously you cannot have service missions. This is very important because even the James Webb Telescope is sitting at the Lagrange point, L2, close to the Gaia point. So Gaia actually gives us a six-dimensional revolution in accurate positions and velocities of stars. We won't talk about that in detail today, but this is just to let you know about all the space telescopes that are there. Now let's come to James Webb. So we saw that there are a whole set of space telescopes which are out there. And would you actually call James Webb the successor to Hubble? Now, the Hubble Space Telescope, let's look at it more in detail. Like I told you, it's a 2.4-meter telescope out in space, which has various instruments. There's an instrument which observes in the infrared, an optical camera, there's a spectrometer, and an ultraviolet spectrograph. Right? And we've actually, I'm not going to go into these details, but you can actually, I think I showed you the various kind of images which we've actually got from Hubble. Hubble has given us really some very beautiful images of the universe. This is the Crab Nebula, and I won't talk about many more of these things, but you can have a look at this, Google, and you can actually see excellent images that Hubble has actually got for us. I will just jump through that because I don't want to spend time, but you can see that there's some very beautiful images that we have through Hubble data. Um, However, let us try to compare the James Webb with Hubble. So the James Webb actually has a size of 6.5 meters, and the Hubble mirror is a single mirror of 2.4 meters, a monolithic structure, while this one is made up of 18 segments. Now, the James Webb is actually an international project which involves NASA, ESA, which is the European Space Agency, as well as the Canadian Space Agency. It's at a cost of about $10 billion. It's a huge this thing. And the purpose of James Webb was basically to study galaxy, star, and star formation in the universe by basically looking back at the universe when the universe was very, very young. Okay, so essentially the purpose of James Webb is to look at faraway objects, faint objects, and that's why you have such a large mirror. And the other important thing was to observe dust clouds, right? Well, if you want to actually look at the early periods of formation of stars and planets, as well as the dark ages, right? You basically want to look through a lot of gas and dust, and therefore it becomes very important that you observe in the infrared. And that is why when people say that James Webb is the successor to Hubble, in principle, that is not right because Hubble was an optical telescope, essentially observing in optical bands, while the James Webb observes in the infrared. And if you remember the earlier list of space telescopes I showed you, there was the Spitzer telescope, which is a 3.5-meter telescope. And in principle, Webb is actually a successor to Spitzer, right? And in that way, it is an improvement on Spitzer and not on the Hubble Space Telescope because it's observing in the infrared. So it also involves a very large amount of expertise, and that is why you needed a collaboration of various space agencies. So NASA, it basically deals with the mirror for the telescope, which is the 18 segment piece, as well as the sunshade to protect the mirror. ESA, ESA's basic contribution is basically was in the launching. So the launching which you saw of James Webb happened at the Arine thing, which is in Kuru, which is in East Guinea, which is in South America, which is an ESA center for launching. That's exactly where Gaia was also launched. And therefore, ESA's job was to handle the launching, as well as one of the instruments on James Webb, which is called the MIRI, which is the mid-infrared detector on this thing. Canada. Canada it actually has a space mission this thing, and actually they are excellent at robotic arms. Okay, so you'll see that a lot of the robotic arms, all that on James Webb is contributed by the Canadian Space Agency, as well as the camera. There's a camera on James Webb called the NIRS, which is the near infrared resolution camera, which is a 4 megapixel camera. This is basically where the Canadian Space Agency has contributed. So the total cost, like I told you, is about 10 billion, but the launch costed 1 billion, which was handled by ESA. Like I told you, there's a big difference in the sizes of the two telescopes, and you can see the big difference in the sizes. So if you were to actually compare Hubble and James Webb, Hubble is actually launched at very close to the Earth. It's just at a height of about 570 kilometers to the Earth, which, like I told you, is that's why it was very easy. It was doable to have service missions. So there have been various service missions which have been done to Hubble to actually make corrections in the telescope. But James Webb has been launched and sent to a position which is at 1.5 million kilometers, which is the Lagrange point, and therefore servicing of the James Webb is almost impossible because it's at a very, it's very far from us. It's at this distance of 1.5 million kilometers. Similarly, Hubble has only a single mirror. James Webb has 18 mirrors, and like I said, that is why James Webb actually had to be folded and launched, and then unfolded when it after it got launched. Right now, let us see a very important other concept about James Webb, and that is related to the study of James Webb. So most of you all, I'm sure, are aware of Edwin Hubble. Hubble was, this is a picture of Hubble observing with Mount Wilson. It's a telescope. And what basically Hubble did is Hubble observed a series of galaxies, observed the spectra of these galaxies. And he actually used the Doppler effect. You know, the Doppler effect actually measures the velocity of a source. So if you have a source and the source is moving away from us, basically the wavelength, if you're observing at a certain wavelength, it gets stretched and it moves towards the redder side. So that is what is called red shifting. So if the source of light moves away from us, it gets red shifted, while if it is moving towards us, it gets blue shifted because it kind of gets pushed and you're looking at smaller wavelengths. And therefore, what happened with Hubble when he observed various galaxies, he could observe the velocities with which these galaxies were moving. And what he found was that all galaxies, excluding Andromeda, seem to be moving away from us. And this is the very basis of what was called the expanding universe. So, what Hubble basically found using the Doppler effect, which I told you, red shifting for moving away and blue shifting for moving towards, he discovered that all these galaxies seem to be moving away from us, and therefore there's an expansion of the universe. Right? And therefore, what happens is that if I want to look back at the early universe, I want to look back at objects which are very far away from us. These are objects which are moving away from us. And that is what we call redshifting. So these objects essentially get redshifted from us, and therefore their wavelengths are towards the infrared side, which is the longer wavelengths. And therefore, if you want to look at the early universe, you basically have to look in the infrared. Now, if you look at the Hubble Space Telescope, the HST, it basically, even in the goods field where you had very deep observations, it could only look at a period which is about, with the age of the universe, about a billion years. Because Hubble looked at the infrared, but it looked only at the near infrared, not in the far infrared. And therefore, it could go to a period of only about 1 billion, when the universe was only about 1 billion years old. Right? But James Webb was actually built to be an infrared telescope. That's the important thing, that it observes in the infrared. Because in the infrared, you can actually look at the early universe, because early universe is going to emit in the infrared, because all this emission from this part of the universe is going to be so redshifted that you will only see it in the infrared part of the spectrum. And therefore, if you want to see this part of the universe close to the dark ages, you have to look in the infrared. And that is why the James Webb observes in the infrared. The other important thing about looking at the infrared is if you want to look at star forming regions or regions where young planets are being formed. These are also very dusty regions where in the optical bands you cannot see anything much. So you have to observe that in the infrared. And therefore, James Webb, while it's trying to study origins, origins of the universe, origins of life, origins of planets, origins of stars, you have to look in the infrared. And James Webb, that's why it was designed to look in the infrared. However, so like if you actually see this image over here, you can see that ground-based observatories, the maximum they can do is look at the age of the universe when it was about 6 billion years old. Hubble went to about 1.5 billion years. Ultra deep field went to about 6-7 billion years. But now with James Webb, you're going to go right almost to to a period which is very early in the formation of the universe, which is a period of about 200 million years, right? And therefore, James Webb will truly be able to probe the early universe because you're looking so far in the infrared. Another example I've put over here to show you why is infrared important. Because, for example, if you look at a source of light, right, which if you're looking at these are the redshifts marked over here. If you are looking at a source of light which has a redshift of about 7.54, 5.74, the redshift is nothing but the delta lambda by del lambda, which is a ratio of the velocity, right, with respect to the velocity of light. So what happens is, if you are looking at a source at a redshift of 7.54, you can see that the redshift, it's located at this part of the spectrum. But if I'm looking at large redshifts, which are objects which are very far away in the universe, which are the early universe, you can see that this part of the spectrum, which should have been over here in the blue part, it shifts to the red and it will come to this part, right? So you can see it somewhere at this wavelength, which is very much in the infrared. So if I want to look at a source which has a very large redshift, I have to actually look at this part of the spectrum. I cannot look at the optical part of the spectrum because the spectrum has shifted to this part, right? And therefore, I have to look at this part of the spectrum, which actually tells me why do I have to look for infrared for the early universe. And therefore, we are coming back to this thing of why. First, I think I convinced you why a telescope, number one. Number two, why go to space? And number three, why look in the infrared? Why? Because infrared lets you look into dusty things, extinct regions. See, here you have an example. This is the Orion Nebula, which many of you all may be familiar with. If you look at it in optical, this is what it's going to look to you like. But if you look at it in the infrared, look at this. You can now see all these dusty regions with the stars and things forming over here, which you can see in the infrared. So if you want to basically look at stars forming, or for example, at the atmospheres of exoplanets, right? You want to do infrared spectroscopy of elements. Supposing you want to look at exoplanets and you want to do spectroscopy of their planets to basically study the composition of their atmospheres, right? This would essentially be in the infrared because there's going to be lots of gas and dust. You have to observe it like that. So if you want to look at these these exoplanets, early stages of star formation or planet formation, you have to do that in the infrared. Similarly, for high redshift sources, these are very old and very distant sources. You again have to look in infrared objects. Also, if you are looking at very young stars which have debris disks around them, that's where planets are forming, where life is being initiated. In that case, again, you have to look in the infrared. And these infrared bands cannot be studied, for example, by the Hubble Space Telescope for the simple reason that Hubble observed in the optical and only the near infrared. Similarly, ground based telescopes cannot observe in the mid infrared or the far infrared because that doesn't pass through the atmosphere. And therefore, you have to go out in space and observe in infrared if you want to observe these kind of objects, right? And similarly, James Webb can also observe planets within 48 hours of a decision. If there is a sudden supernova burst or a gamma ray burst, it can observe it immediately. So if you were to look at the same part of the sky, this is invisible. This is how it will actually look to you in the infrared. So you can see that the number of stars, these are regions of star formation, star forming regions, where young stars are formed. You can see that most of the stars get covered because of the gas and dust. But if you were to observe them in the infrared, you can actually see these stars, right? You can see these stars over here in the infrared very clearly because of observing in this, right? So if you were to actually look in wavelengths, Hubble observes within this wavelength range of zero point 0.1 microns to less than a micron. James Webb is going to observe in this wavelength range, while Spitzer has, observed way beyond over here. And therefore, if you were to look at the same telescope, you would actually have so much of an advantage of looking in the infrared. So, like I told you, in principle, Webb is actually a complementary or improvement of the Herschel Space Telescope. Herschel was is a 3.5 meter telescope which observed in the near far infrared, mid far infrared, from 55 to 650 micrometers, while Webb is 6.5 meters. It's observing in zero point 0.6 to 28.5 micrometers. And in this way, you actually look for the extremes using the telescope. Now, what is the important? So yes, we do need infrared. Now, what is the problem by having infrared telescope? If you have infrared, uh, you may be aware that we are also very good infrared emitters. The Earth is an infrared emitter. The Moon is an infrared emitter. And therefore, if you want to have a telescope in the infrared, it essentially has to. You can see here is a video of how the James Webb Telescope was actually made. And like I told you it actually had to be made in a cryogenic vacuum chamber, which you can see over here. And the mirror is made up of 18 segments. You actually have this vacuum environment in which you produce these very well made mirrors. And the very important thing is that these mirrors have to be made in such a way that they are protected from infrared light, right? So, if you can actually see, this is how the mirrors are being prepared. And they are made up of, if you see what we've been calling the golden eye, this is actually made up of a thin gold coating, because gold very well reflects infrared light, right? And therefore it's good to have it. It's made up of a hexagonal segments. Each segment has a size of 1.3 meters, made up of 18 segments. Each segment has a weight of 20 kgs. It has a secondary mirror, which is there, which has a size of 0.74 meters. And you have what are called accentuators. Accentuators are made to actually position the mirrors, because what happens is when you have a hexagonal array like this of mirrors, you essentially have to use that to align the mirrors perfectly in space, right? So these are the accentuators which are placed over which you have the segments placed. Okay, so the mirror segments are placed on top of these accentuators, and the segment gets placed on that, and the accentuators kind of can align the mirrors. They have to align it to the precision of the thickness of a human hair, right? The diameter of a human hair. It has to be so well aligned, right? So that these mirrors together make up a perfect lens, right? So these 18 pieces are put together. The accentuators balance it to make a perfect mirror. This is the secondary mirror, which is the focus point of this mirror, the primary mirror, right? So the primary mirror gives you then the image. It focuses the images onto the secondary mirror, right? And it has to be very perfectly aligned so that the images of all these mirrors fall on the central point, which is the secondary mirror. And that's this whole business about alignment of the mirrors. So you have to perfectly align the mirrors so that the images of all fall onto the secondary image. The other important part about this is that because of infrared, you have to cool the whole telescope. So the telescope is cooled using cryogenic technology, and obviously it has to survive the rocket launch. It is going to a position which is very far from the Earth and the Moon, 1.5 million kilometers, and there are very effective sun shields which will protect the telescope from sun rays as well as rays of the Earth, etc. Right? So this is the primary mirror segment. This is the secondary mirror segment. There's a tertiary mirror also and a steering mirror. So all these are the important components. You can see the light path which is there. So if light falls onto the primary mirror, which is positioned over here, you can see it focuses and comes onto the secondary mirror, which you can see over there. From the secondary mirror, it falls on the tertiary mirror. And the tertiary mirror will then send it onto the instruments where the readings are taken or where the detectors are placed. Now, the important component is the sun shield. So, if you look at the sun shield, it has a size of about 20 mirrors across, 20 meters across. And you can see that the sun shield actually opens up. So, in the launch, it was folded, but then it has to actually open up so that it can protect the telescope and its components from the heat of the sun, the earth, and the moon. And it's basically made up of 5 layers. So, there are 5 layers. Each layer is as thin as a human hair. It's made up of a specific material called Kapton E, and this is a polyimide film, okay, in such a way that these membranes are specially coated with this material where you actually do not list it. Now, accidental tears can take place, obviously, of this material because it's very, very thin. And that's just what has happened in 2018, that there was a tear in one of these, in these sheets, due to which they had to actually postpone the launch of the telescope because the shield had to be redone to make up for this. And with this, you can actually achieve a temperature of 26 Kelvin. This is a temperature of about minus 230, minus 230 degrees centigrade or 36-degree Kelvin. So essentially, you have this, I should show you that once again. You basically have this layers, 5 layers, right, which will actually make this thing, and therefore you can place these things, right? So you will have these 5, and that's the important job of this because it basically has to protect the telescope as well as the mirror and all the components, because finally you want to achieve a temperature which is less than less than 50 degrees absolute zero, and therefore the sun shield is a very important component of the telescope because it protects it from all these other components, right? Now, the other important thing, like I told you, to protect the thing was to place the telescope at the L2 point, right? So if you actually have the Earth and the Sun, the L2 point is the point which is, I'll stop the video so that you can see it better. Let us just see the video. So you actually have, this is the Earth going around the Sun, right? And the L2 point is the one in which you can see over here the gravitational force gets balanced. So the James Webb is placed over here at this L2 point so that it is never going to face the sun. It's always going to be shielded by the sun shield. It will sit over here and will never get exposed to sun rays. And this L2 point is at a distance of 1.5 million kilometers, right? And that is what is over here. So if you want to actually know where is Webb, right, I can show you a very simple way of finding where is Webb. Where Webb is against the sun. It is where the sun is not there. So for example, if you were to look at the moon, you know that the horns of the moon this points a direction away from the sun. And this is exactly where Webb is. So Webb is at a direction which is away from the sun. If you look at the moon, the horns of the moon, this is the direction of the sun, and Webb is sitting somewhere over here. So essentially, in the beginning time, when Webb was launched, the first month of Webb, if people wanted to actually look for Webb, they would actually look at this part of this thing. And people did manage to actually get images of Webb when it was just launched, when it was closer to the Earth. Now, obviously, it cannot because it's very far away, so you do not see it. So all you need to know is look at the moon, see the horns of the moon, right? And it's going to be on that side, the non-sun side of this thing, right? Now, what are the instruments on Webb? So Webb has a camera called the near-infrared camera, which was made by the University of Arizona. It has a near-infrared spectrograph, which was made by ESA. This is the NIRES thing. Then the MIRI instrument, which is made by the Jet Propulsion Lab as well as ESA. And then there's a flight guidance sensor with a tunable filter module, which was made by the Canadian Space Agency. So here is the primary mirror, the secondary mirror, the tertiary mirror, the sun shield, and you have the different instruments placed over here, right? So you can see it more in detail. We don't have time to go into each of these instruments, but each of these instruments are a total engineering feat in the way they were actually built. It's actually an engineering wonder. So I could even show you this short video where you can actually see how beautifully, this is just a time lapse of how James Webb was made. And so this is a time-lapse video of the making of James Webb. And okay, it's a nice video. So you can actually see the precision with which it was actually, assembled, the whole this thing. And imagine the scale. This is a scale where the telescope itself is 6.5 meters, right? And along with that, you actually install the whole thing. It has to be very beautifully, very precisely made in such a way that it can be unfolded after the launch. So the whole telescope has to bear the rocket launch and then unfold itself to actually perfectly observe with the precision that is required of it, right? So it's truly an engineering wonder if you think of the way it, this thing, which actually tells it's a good thing for students that if you're interested in the field of astronomy, you can contribute at various levels. You could be doing the astronomy, but you could also be playing a very important role as an engineer in actually building of these instruments and how it's actually done, right? That's also a very important component in how it's actually made. So if you actually see when they packed up the instrument, you can actually see how the instrument was made. Like I told you, is this is the instrument, right? It literally had to be packed or folded. It was folded in such a way so that it could be packed and it could be put into the tower where it's going to be launched, right? So before the launch, it was folded, packed up, and put. So these are the sun shields, which you can see, the silver shiny stuff. The yellow, the golden part is obviously the telescope. And with that, it was actually folded and made, right? And so you had the folded telescope made, which was sent for the launch. This launch was in South America, right, and near the coast. And therefore, actually, what James Webb had to do was, after it was folded, it was actually put on a barge, in which it actually went to French Guiana, right? It was a 16-day journey while it went on this barge over there to Kourou, right, in French Guiana, where you actually had the launch. So it did this thing. And then after it gets launched, you had a 1 month thing where it actually traveled this distance of 1.5 million kilometers, which was the L2 point. So there was a whole time sequence of how after the launch, you had first of all the solar array had to be deployed. Then there's the antenna, which would give the ground-based commands. Then you had a sun shield, which was there, that had to open up, right? Nothing could go wrong in this. Then the primary mirror had to open up, the secondary mirror had to open up, and that's when it moved towards the L2 point. This took a whole month. So in a month, it actually reached the L2 point. After it reached the L2 point, the other important thing was about cooling, right? You needed to cool it. First thing was to align the mirrors. So I told you the precision at which the mirrors had to be aligned was to the precision of, of uh, the the precision of hair that well. And uh, and then it had to obviously yeah, I think there's a sound. Yeah, so is this fine? I think it's a small this thing. Is it all fine? So Supandeep, can you, everything is fine or no? Because my thing seems to have paused. Is everything
Yes,
okay?
ma'am. There was a pause in your video, but now it is fine.
Okay, now it's fine. Okay. So I'll have to reshare, no? I think I'll have to reshare.
Just reshare because the screen is stuck.
Yeah. I'll just a minute. Just a minute. Okay, I'll have to do stop presenting and then I'll say present my entire screen. Okay, now it's good? Now fine?
Yes, ma'am. It is visible now.
Okay, so in short, it had to do this long journey to the L2 point, which you can see over here. And JWST, the whole deployment had to take place. Like I said, it was a very precise thing. It had to be done with real perfection. So there were a lot of, this thing, this was the last view of JWST when it was launched. Now, the early science programs, what we are meeting for today is talking about the early science programs. So obviously, the early science programs included things on exoplanets, on stars, on galaxies, on dark matter, etc. And therefore, Webb actually planned its first cosmic targets. So during the 6 month period from the launch to today, basically the mirrors were aligned, the cameras had to be cooled. They had to be cooled to a temperature of about 30 absolute zero, 30 degree Kelvin, which is absolute zero, close to absolute zero. And they had to, so the first targets were actually declared. These were the targets mentioned over here, which you had Eta Carina. This is Eta Carina. This is a star-forming region. So, like I told you, this is the ideal kind of object to observe with James Webb because it's dusty. You cannot see it very well with optical, so it would be very good to observe it with infrared. The second one was this is Stephen's Quintet, which is a cluster of galaxies, and this was one of the targets for James Webb. The other one was WASP. This is a gas giant to basically see how well can we do the spectroscopy. And then the Southern Ring Nebula. This is a ring nebula. And the other important image, which is SMAX. So SMAX is basically a galaxy cluster, which is at a very large redshift. And this was the image which was actually released yesterday. So this was released by the President of America, Joe Biden. And this was an image taken by the near-infrared camera, which was an exposure of 12 and a half hours. Now, just to tell you, give you an idea of the capability of James Webb, essentially, this was literally a slice of the universe. In the sense, this is supposed to, this field which you're seeing is the size of a grain of sand. If you were to hold a grain of sand at arm's length, right, by someone on the ground, and you were to look at it, this is the kind of field of view which we are talking about. Okay, this is so tiny. This is the field of view with which you can see it. Now, this is a cluster of galaxies which is very massive. And we know that mass, in principle, gravity, can actually act like as a lens, right? So you know that light bends because of lenses. But sometimes, in certain cases, the gravitational force, right? If you have a very massive object, it can actually bend light, right? Just by its gravitational force. And this cluster of galaxies, it's so massive that if you look over here, you can see these arcs. I hope you can see these arcs of light. And these arcs of light are basically images caused by gravitational lensing. So you have basically a galaxy which is giving you multiple images over here. Look at this: one, two, three, four, five, six, seven. These are all lensed images of a galaxy because of the mass which is sitting in front of it. So this was the first image which was released yesterday to give you an idea of the kind of science you're going to get with James Webb, right? So this is really amazing. This is one of the most. This is the most deepest infrared image ever taken of anything from the Earth, right? So this is the image which was released yesterday, and today is the day when NASA is actually going to release those first light images, which I mentioned over here, which are these ones: Eta Carina, Stephen's Quintet, WASP, as well as the Southern Ring Nebula, and a whole bunch of other early images. They are going to be released today at 8 p.m. IST, and because of the time difference, it's our evening. But that would be good, and that is the purpose of the talk which we have today. Which I thank Hex-Star for giving me this opportunity, because I've actually hopefully tried to tell you what James Webb is all about and what you should be actually seeing today evening at 8 p.m. So go to this website, which is at NASA.gov, which will show you web first images. If you forget this website, no problem. You can just Google first images of Webb, and you'll be able to see it today in the evening at 8 p.m. IST. And I think that would be a very, people are actually comparing it to, this would be something, close to even what when Galileo first looked through his telescope, the kind of things he saw. That is the kind of jump we are going to have today with the images we are going to see today in the night tonight, or at 8 p.m., which we are going to see the first images of James Webb. And unfortunately, I can't show them to you just now because I'm waiting to see them tonight. But I think it's going to be really a very interesting thing to actually look at those images. You can, I think it would be something beyond our imagination. And we are all very strongly looking forward to the kind of science we are going to get using James Webb, and because it's going to be operational at least for the next 5 or 10 years. And with Hubble itself, we had a lot happening. There's a lot more in the pipeline also. There's a Nancy Grace Roman telescope, which is going to be launched in 2027. There's the Euclid telescope. Then there's another Super Hubble, which would be the true sequel to Hubble Space Telescope, which will again be another 6-meter telescope for which people are still looking for funding. And it is definitely a very exciting time for astronomers with all these new path-breaking telescopes which are coming in. And I think it's going to be very exciting. So we all look forward to these images. And I would urge you to actually have a look at these images tonight. And it's going to be really very interesting. So I'd be happy to take any questions. And thank you.
Thank you, Priya ma'am. That was a wonderful session by you. And I think there are some questions in the chat.
Yeah.
First, you can take the questions from the chat. Then if anybody is willing to ask the questions, they can turn on their microphone and ask the questions.
Yeah. So I can. Okay, so the first question is, what is the material of James Webb made up of? So, like I told you, different parts are made up of different material. The sun shield is made up of a specific material. The basic telescope, if that's what you are interested in, that is of a specific material. Though there's a gold coating, and this material, I can just a minute. I will actually look at the material. There's a name of the material. I can just tell you 1 minute. Yeah. So it's beryllium. It's essentially beryllium of which it's made up because beryllium is strong and light and the ideal material to actually make these mirrors from. So that's it. Okay, the other thing, what will be the final image of Webb? I'm not too sure. What do you mean by the final image of Webb? The final image of Webb, which I showed you, was the image which we saw, the last one when we saw, Webb was moving away from the Earth. That was this thing. But now Webb is going to begin its operations, right? Because till now it was still doing calibration, alignment of the mirrors, cooling of the instruments. It was doing things like that. While now it's actually going to, observe all kinds of things. So Webb is a target-based observatory in the sense people actually have to write proposals. So if you want to observe something with Webb, it is open to anybody anywhere in the world. You can write a proposal to observe with Webb. And then there is what is called a time allocation committee. So the committee will actually look at your proposal, at what do you want to look, and accordingly, it will actually, you can actually be allotted time on the James Webb, and accordingly this thing. So the final image will be, something which will come depending on this thing. There's another question, how far back will Webb see? So Webb is going to look in the earliest part of our universe. It's going to go back to a time when the universe was only 200 million years old. So it's going to look back at a very early stage of the universe, the furthest till now ever been possible. No telescope has been able to look back. So it's going to look at the universe in the earliest stage we've ever been able to look at. We've never looked at it in that stage. Soham Deshpande asked me which telescope is used for the mission SETI. So essentially for SETI, people use radio telescopes because the idea is to look for intelligent life, which is sending some kinds of signals, because otherwise we just don't know where to look, right? So typically radio telescopes are part of the SETI mission. So Arecibo telescope, which was in Puerto Rico, that was very, active in the SETI mission. If you've seen the movie Contact, in Contact, they show Arecibo being used for SETI, but Arecibo was actually used for it. GMRT is being used, the Indian GMRT, but not so often, but not so. Essentially, radio telescopes are used for SETI. JWST will not be used for SETI. JWST can be used to study the atmospheres of exoplanets. So exoplanet candidates can be identified using Kepler and TESS. I showed you those two space telescopes which basically look for exoplanets. So you can find them candidates using Kepler and TESS. And what this James Webb can do is actually do further targeted observations of those exoplanets. So there are various methods in which you can use Kepler and TESS data to actually get masses, radii, density of planets, right? And what James Webb will do is further explore those planets which are identified by Kepler and TESS, as well as ground-based missions, right? So Trilok Varshe asked me, please tell some galaxy name which are blue shifted except Andromeda. So I've heard only these few. Okay. So even I am not too sure of other than Andromeda, which are the other blue shifted galaxies, because essentially what Hubble found is he found all galaxies to be red shifted, right? So blue shifted galaxies, are there other galaxies with, okay, so there are some. So there are some which are blue shifted. You can Google and find them. So it says that there are about 100 known galaxies with blue shifts out of the billions of galaxies. So the bulk of them are all red shifted, but there are about 100 which are blue shifted. So blue shifted is also there. Um, it does exist, right? Soham Banerjee asks, okay, oh, he says the Great Triangulum Galaxy is this thing. Okay, 32%. Okay. Teja Brigari is asking me, from this end, really excited for the meet. Okay, great. That's right. So my question is, 13 billion years ago, space was small. How do I imagine and correlate my photo to my imagination? So uh, the photo to my image. So actually, yes, I agree that space, but we are actually not, even with James Webb, we are not going to go to 13 billion years. We are going to go to about 200 million years, which is still a sizable universe. So it is still not absolutely that small. So with James Webb also, we are still going to go to a sizable universe, not that small. We are not going to go to the point where it was a point. So that's not this thing. Yeah. So I think, Somadeep, I've covered all the chat questions. If there are any more, you can let me know.
Yes, ma'am. I will just ask.
Ma'am,
Okay, okay, okay. Okay, Trilok, you're happy to open your mic and ask your question.
thank you. Ma'am, which is the most acceptable rate expansion rate of universe, like by
Okay.
shoes method or CMB analysis, like 73 plus minus 1 0.73 plus minus mega per sec, kilometer per sec per mega per sec. So,
Yeah.
which is the most acceptable rate of expansion of universe? Means Hubble constant value.
Yeah, yeah. So actually, the biggest problem with Hubble's constant that in principle it's not a constant now, right? Because we know that the expansion of the universe is taking place with an acceleration, right? So with Hubble's constant, you're assuming that it's a constant expansion rate, right? Constant expansion. But what we
Yes,
know
ma'am.
now is that this expansion is taking place with an acceleration. So in principle, Hubble's constant is not a constant. And therefore, what happens is when you observe it using different methods, you get different values because actually there is an accelerated expansion of the universe. It's not expansion of the universe, it's accelerated expansion. And therefore, obviously, there's a problem with, depending upon the method, the different values you mentioned, they are achieved using different methods, right? But we do not know which is the, which is the right, it's not a question about the right method, but which is the which is the most applicable, because there could be different ways in which you are exploring it. And like I said, that because there is acceleration taking place in the universe, which is basically happening because of anti-gravity, right, which we cannot characterize, right, we do not know how is that actually happening. It is very difficult to this thing. So generally people take a 75 kind of value, 73, 75. That is the kind of acceptable value we take for Hubble's constant. But like I said, number one, it's not a constant. And number two, it is method dependent. So in principle, I do not have the answer to your question as to what is the right value. We do not know. We do not know. It is
Yeah, ma'am.
within
I just
that
want to ask. Yeah, ma'am.
with certain errors, but we do not
Yes,
know.
ma'am.
Yeah. Okay.
Yeah, ma'am. I just want to ask which method is more accurate between the CMB analysis and shoes analysis. That's all my question.
Uh, uh, I will not. I'm not an authority to talk about it because I don't do CMB and I don't do shoes. So I think it's better I don't say. You should ask someone who this thing, because obviously each of the groups will support their
Okay, thank
method.
you, ma'am.
I don't want to. This thing.
I think there is one more question in the chat.
Yeah, yeah, sure. Okay, I'll just, yeah, I can see. Can you please share the video? Yeah, okay, I can share you the PDF. So I don't know, Ravi Shankar, I don't know exactly which video you are talking about because I had lots of embedded videos, but all of them are free videos available on YouTube. So if you want to find any of them, you'll find them on YouTube. They're all there on YouTube. I can share my presentation, so you can have that, but the videos are all there. Yeah, okay.
If anybody from the chat is willing to ask questions using the microphone, please do it now. Okay. So I would now just request one of our moderators to collect the questions from other social media platforms and paste it in the chat so that ma'am can answer these questions also.
Ma'am, can you ask about El Pizarro mission, future mission?
Which
ELST, El Pizarro.
ELST? I don't know about this mission. What is this mission about?
It's a mission about the study of comet. Like it's a
Okay,
different type of comet. Is it an asteroid or comet? Like El Pizarro mission, future
okay,
sun mission.
okay. Sorry, I don't know much about it. You'll have to Google because I can only Google and find out. I don't know. I'm sorry.
First question is in the chat now.
Yeah, okay, one sec. What is the maximum range of James Webb? I don't understand. What do you mean by what do you mean by range? You mean to say range of wavelengths or range of distance or range of what? Hello. Please, could you answer the question? I didn't understand. What do you mean by range?
Ma'am, I think that the question is from the YouTube, so
Okay. So if you're talking in terms of distance, which may be the thing, it will go to a redshift about 15. So it's going to go to a redshift of about 15. Okay. If that's what you want, or in terms of the age of the universe to the age of the universe, about 200 million years. That is the range of that's the distance, the redshift 15. Yeah. So it's about that. Oh, okay. Kasturbe has another question. Why is the shape of James Webb like a honeycomb? Okay, that's a very nice question. So the problem is actually in building mirrors, right? So actually with James Webb, there are two problems. One is about building mirrors. So it is easier, relatively easier to make a single mirror of about 1 to 2 meters, right? But to make a single mirror of 6.5 meters is very, very difficult because the problem is you want accuracy, you need accuracy of the wavelength of light, right, for the mirror to be smooth enough. The other problem with James Webb is that since it was to be sent on this Ariane rocket, okay, in the Ariane rocket, like I showed you right in the beginning, you could not fit the James Webb if it was in open condition, right? It's like a two-story building, James Webb. It's so huge, right? So it could not fit onto on that, to be launched, and therefore, it one problem, like I told you, was to make a big mirror. It's easier to make smaller mirrors, and number two, even if you could make a 6 meter mirror, we could not launch it. We don't have a launch vehicle which will take a 6 meter mirror. So we had to fold the mirror, and therefore the mirror was folded. So if you remember, when you saw the images, the James Webb was folded, and after it was launched, it actually had to unfold itself, right? Because otherwise it was in a folded condition. So both reasons are there. One is honeycomb is the standard design which is used for telescopes larger than 2 meter, 3 meter. If you want to make a 6 meter telescope or the 8 meter telescope, generally you make it with a honeycomb structure because then you can make smaller pieces and add it. And honeycomb, has, if you know what is packing fraction, There is a telescope which is called a GMT, which is made up of seven circular mirrors. But then you'll have holes in between. But if you do honeycomb structure, then you can have a mirror with minimum gaps, right? There'll be most of it will be covered. So the packing fraction is very good if you have honeycomb structure. And therefore, for larger size mirrors, 6 meter type of mirrors, honeycomb is only what is used rather than having a single, a single piece. So that is the idea. So one is for 6 feet, 6.5 meter, and number two because of the launching. So you need this thing. Okay. So there's another one from Ashish Rajguru. Do you believe that multiverse is existing? I think Marvel Comics seem to love multiverses. All the Spider-Mans and Doctor Stranges are all in multiverses. But in principle, a multiverse, mathematically, you can have such a structure, right? You can have such a structure, but obviously, we have no indication or no, what do you say, observational evidence of a multiverse. So I don't. So in principle, they can exist, but I wouldn't want to comment on it. So mathematically you can have a multi-dimensional universe, right? You can have 100-dimensional universe, but whether it actually physically exists is something we do not know. So about multiverses, also I say mathematically as a theoretical construct, it can be, but whether it really exists is another story. So that we don't know. Um, so Ravi Shankar, I'll send the presentation to the organizers, and they will share it with you, right?
Okay, okay, madam. Okay.
Yeah. Teja asked, does NASA coloring department add colors to James Webb as they do to Hubble images? So, see, they don't add, the coloring is just meant for display of the image. It's all image visualization tools which are used in astronomy have artificial coloring. So they have, color maps. They are called color maps. So these are all data or image visualization tools which have color maps. So NASA does not have a coloring department. Okay, there is no coloring department of NASA. There is color maps which are used by different image display or image visualization tools, and depending on that, the color maps can vary. So even if you download James Webb data, you yourself can add the colors you want depending upon what color map you add, right? And therefore, it's not NASA coloring department. It is just the visualization tool which you add. Like if you've seen there was an earlier image of James Webb which showed orange stars, right? So there's a certain color map called heat map. So if you use heat map, you get that kind of a color. But in principle, you could have made your stars look blue or green or whatever color you want. It does not mean that the stars were orange in color. They were not. That's just the visualization tool which has color maps, right? So that's just how you visualize the images. You will change the color and accordingly get your color maps, right? Ashish, same. I'll send the presentation to the organizers and they will share it. Teja again asked, can you please give a small gist of how exactly these colors? Yeah. So the colors are added by the color maps and accordingly they happen. Another question Teja has is something I found interesting is the direction of curvature of those curved directions. The curvature seems to be oriented towards the center. Correct. So basically there's a galaxy cluster which has a certain mass which is causing the bending, and the center of mass is obviously at the center, and therefore the lensing of the galaxies was aligned towards that. So that's a good observation that it was aligned towards the center because the center of mass of the galaxy was in that center. So that can be used to kind of identify where is the center of mass of that cluster of galaxies. So we want to identify where's the center of mass. It's sitting somewhere in that region, right, where you actually see this thing. Triloka Varshri has a question on the Lagrange points. Why are we putting a telescope at L2 point between all 5 points? Okay, so that's also a very good question. So actually there are 5 points. The L1 point is actually the point between the sun and the earth. So from the L1 point, you would always be able to see the sun. So for example, there is a mission called Aditya, which ISRO is launching this year or next year, which is specifically for observations of the sun. And that mission is being sent to the L1 point, because it is a point where you are going to always see the sun. The L2 point is a point at which you are behind the, you are not going to see the sun. You are seeing it, there's an earth between the sun. So there's the sun, there's the earth, and the L2 point. So L2 point doesn't see the sun because it's the earth comes in between. So L2 is where you actually need to put a telescope which does not want sunlight. And since this is an infrared telescope, we do not want sunlight, definitely. So even Gaia, the earlier telescope I talked to you about, that is also at the L2 point because you don't want the sunlight to fall there. So you have it over there. It's kind of, the earth is in between, plus you have the sun shield, which will protect it. Right? So that's why you need to keep it at L2. The other points are much more further away, and therefore it would be more difficult to send it to those points, though those also exist and they could be used. But L2 is the closest point which can be used. Yeah. Sumadeep, are there any more questions?
I think all the questions are done from the chat. And for the last time, if anybody is having any other questions, please open your microphone and ask the questions.
Yeah.
Okay, so as no one else is having any other questions, so I'd like to conclude the session. Before concluding, I would like to say a few words. Yes, before ending the session, I would like to tell you and let you all know that we are arranging for various events regarding the International Moon Day, which is on 20th of this month, where we will have space talks, quiz, and a live streaming session where we'll try to showcase the images of the moon via our telescope. And in the month of August, we are also arranging for a master class, which is on rocketry. So if you want to keep track of all of these things, please follow us on our social media handles, and you can always also check out our website, that is www.hexstaruniverse.com. And this was all from my side. And thank you, ma'am, for this wonderful session. I think this was really a great session to have, and we would like a few more from you. Ma'am, you're not audible.
I muted myself because I did want to
Okay,
add
ma'am.
the
Okay, no
question. Yeah.
problem.
Yeah, my pleasure. I'm happy to be there, and thank you so much. Thanks for calling.
Thank you, ma'am. Thank you, ma'am. It was a great session.
Thank you, madam.
Thank you, ma'am, for a great session. Thank you.
Thank you.
And lastly, please, everyone, if you can turn on your camera, we'd like to have the screenshot as a memory purpose. Thank you, everyone. Thank you. Yeah. I've taken the pictures. You can just leave the
Okay.
meeting now. Thank you, ma'am.
Yeah.
Once
Thank
again.
you. Bye-bye. Yeah. Thank you.